Welcome today to this week's webinar, which is titled Fan Systems, Duct Design and System Troubleshooting. So I'm James Neal and we'll be hosting the webinar today. So what we're going to do briefly today is we're just going to quick overview of fan systems in terms of how we break it down. We're going to look specifically around fan inlet ducts and then exit ducts and exit conditions. Then we're going to look at duct transitions and bends and how these impact on various parts of the system, and then a couple of case studies to round out the webinar. And then, as I mentioned, we'll have an opportunity for some questions. Okay, so just getting our heads straight, I always like bringing things back to the old compressed air analogy where you've got a supply, distribution and demand or end use. In much the same way, in our fan system, we'll have a fan, i.e. or multiple fans, and these could be in series or parallel, and then obviously they are connected to the various end use points or processes that are using that air or other gas stream that may not be air via various bits of ducting and so forth. Now typically the ducting isn't the desired destination of the mechanical energy imparted by the fan. It's purely a means of transmitting or conveying either the air or other species for a reaction, or in other cases it is actually a part of conveying a product or moving a product or various different parts of a product to then go to some sort of reaction vessel or dryer or some other pieces of equipment. And typically, as it says down the bottom there, your ducting is going to form part of the parasitic load on the system. So an ideal good design is going to minimize these parasitic loads or transport losses, and at the same time, and we're going to really hammer this point today over and over, the importance that if you get the ducting right, your process will normally run that much better. And so it's not just about saving energy, it's as much, actually more so, about getting it right so that whatever you're using the air or fan to do can actually work to its full extent that it's intended. Now, of course, the other side of the coin as well is various systems typically will have some sort of cyclone or dust extraction baghouse, if you will, as part of these systems, especially nowadays, tightening environmental resource consent constraints and so forth mean that emissions into the atmosphere is much more tightly controlled. And the reality is bad duct design can make a really good cyclone or baghouse perform really badly, whereas if you get the ducting right, generally these pieces of kit work just that much better. Okay, so in big terms, big picture, the duct design is heavily impacting on the efficiency of the system. Now, you might have a premium efficiency fan. You might have paid for a good quality fan from a reputable manufacturer with a really good aerodynamically designed and optimized, tuned impeller, nicely balanced, correctly suited for the speed that you're going to run it at. The fan housing could be well engineered. Everything could be absolutely wonderful at the fan end, but if then we hook that fan up to poor ducting, poor flow transitions, and have generally bad flow through our process and various unit operations, the overall efficiency of the system can end up being very, very poor. So it's not uncommon to see 30 to 80% of the fan energy, so that's the shaft power going into the fan, being wasted on transport and distribution as opposed to actual end use. Not too dissimilar to some of you that are thinking, gee, I thought compressed air was the only sort of system that can waste a lot of energy. Well, a badly designed fan system can be just as bad. Now, you can waste all the efficiency gains that you can make by having good fan selection by mucking up the design of the rest of the system. So the fan is only part of the system, so we need to consider in particular the inlet and exit conditions of the fan. So very, very important here. Can't emphasize this enough. You can once again spend all this money on having a really good quality fan, but then if you put a really bad fan intake, poorly designed inlet filter bank, for example, you can compromise the performance of that fan. Similarly, if you've got a really bad outlet to the fan or really poor duct transition from there to where the air's got to go, might be that the fan's in a really tight spot in the factory, and sort of you have to compromise on the duct design. If you don't get that duct design right, once again you can foul the whole nest. Now, one of the key things with fan exit conditions is generally a fan generates quite a bit of dynamic pressure in the form of a high velocity air coming out of the fan, and how well you convert that dynamic pressure or dynamic head back into static pressure is going to determine very much the efficiency of your fan in relation to the system and what it can do. And often what we term that as static pressure recovery. Now, suitable duct sizing, transitions and bend design can minimize these losses in a transport system. Okay, but once again, you might be compromised on space, but there's some tricks you can use that we'll talk about today so that you can, even when you're faced in the real world, we can appreciate that costs of buildings that these plants fit in generally have a big say in dictating where things go. And so if you're doing these sorts of things, or you've got those sorts of design compromises that you have to worry about, even in a retrofit situation, you know, it's something that you don't have to just throw your hands in the air and say, well, it's what we have to live with. What you can do is there are some tools that you can put in place, some strategies you can deploy that will enable you to minimize those losses. Okay, so key point, and I'll reiterate this throughout the webinar today, poor ducting will compromise the functional performance of your system if you're not careful. So what I really want to talk to, and we've used this diagram a number of times over a series of webinars, and what it comes back to is if you think about a product going out the door, it could be some milk powder, could be some pulp, could be some steel, could be any widget that you're processing, fertilizer, any particular product, or it might actually be just your air conditioning system in your office building. You know, if you look at what your product, be it air for environmental conditions or your process, whatever it is you're doing, there's a minimum amount of energy highlighted in green that you're going to use, okay, to do what you need to do. Now, the first lot of losses, which is the yellow block, is maintenance and housekeeping. And we're not really talking about that side of the equation today, but we've talked about that previously. The second one in blue is how we run the plant, so very much more about our process, operation and control decisions. Once again, not a key focus on today's webinar, but what we are really going to hit on is this third one, which is the big red block there, which is really how things are designed. And often we look at these things and we say, oh look, well it's built into design, there's not much we can do about it, we just have to accept it. And really the take-home message for today is really one of actually, at the end of the day, in a lot of instances, it can actually be very worthwhile to do something about some of these problems, and in most cases it's something that can be fairly easily modified or integrated or reintegrated as you upgrade your systems. Now, one of the key points here, of course, is generally, in most cases, and we've got a couple of case studies we'll share at the end of the webinar today, the energy savings alone don't pay for the modifications, but we'll go through today and you'll see that some of the other savings are more than adequate to pay for these modifications. Okay, so we're going to start today looking at fan inlet conditions. Now, the inlet condition to the fan can be very, very important. Okay, now a poor inlet condition does a couple of things. First of all, it can decrease the effectiveness and the efficiency at which the fan imparts energy to the system. And so some of these issues arise from fan control, how you're controlling. For example, you might have variable inlet guide vanes at the front of the fan, which is a little bit better than just sort of having a knife that you just sort of slowly pull back. A single butterfly, especially if that butterfly is too close to the fan, can cause all sorts of problems. So ultimately what you're trying to do is ensure that you get good, even airflow coming into the impeller on the fan. And like any piece of rotating machinery, if you have an imbalance in the load on that impeller, that's going to not only create inefficiencies, it can also create maintenance headaches in terms of imbalance and high vibration levels, which can be detrimental to the life of the equipment. So One of the really good examples of this is, I apologise, the graphic could be a little better. If you have a ducted inlet to the fan, so you can see here that both fans in the picture here are rotating in a clockwise direction, and you can see that we have a clockwise rotation on the duct, and so ultimately this duct is putting a bit of pre-rotation swirl on the intake to the fan. Now by and large that might be okay. However, what you'll generally find, especially if these are square ducts and you'll have all these dead spots in the corners, you'll have all sorts of eddies, and if you get this wrong you can have an eddy in the wrong spot and you can actually cause part of the impeller to stall. I've seen situations where the whole front end of the fan causes the duct to vibrate, which causes the wall to vibrate, which has then gone right through and caused the ductwork downstream of the fan to vibrate violently and caused all manner of damage to plant and equipment and created all sorts of safety hazards, to the point where sheets of steel have been but literally shaken loose. Now obviously there are certain things where maybe some of those sheets of steel should have been better secured, and people were perhaps not quite giving due diligence to getting their design right, but it's very, very important that you get the intake to the fan aligned with the fan intake itself. Now as an example or comparison here, so here's a plan view and a side view. So the one on the left, obviously the rotation and the flow is aligned with the impeller rotation. And the one on the left, it actually ends up rotating against the rotation of the impeller, which can cause all manner of challenges and issues. So these are the sorts of things you have to be very, very careful. So from a troubleshooting point of view, if you've got a high vibration around your fan, or the ducts seem to be moving, the first thing to start looking for is just have a look at the orientation of the duct and try and visualize, well, where's the air going, what's it trying to do, and is it actually working with or is it fighting against the system. Now so obviously just on this, just to summarize that, if you have a co-rotating swirl, it's going to decrease the pressure volume, i.e. the fan curve, dependent on the intensity of the vortex. Now if you have a counter-rotating swirl, okay, that's going to cause all sorts of pressure increases, and it's going to be a large power increase for the fan to move the same amount of air. So you're going to have to speed that fan up quite a way, pull a lot more power, and obviously the dynamic loading and everything's going to go up, so you need to be careful. You could start to run into damaging impellers, especially if you're running up close to the maximum design speeds of the equipment. So the ideal inlet is an actual flow without swirl. If you do have swirl, you want to think very carefully about, do I need to put some flow straighteners in there to eliminate or reduce the impact of that swirl? If you've got a crazy ducted design, you might need to actually deliberately put some flow straighteners to disrupt the inducing of eddies at the front end, or vortices at the front end of the fan. Like I said, the fan I mentioned previously that had a high vibration at the inlet, they were treating it as an open inlet, but the cavity that was feeding the fan was actually quite tight, so it ended up behaving like a ducted inlet, and there were some really nasty vortices induced in just the wrong spot in the duct. So you have to be very, very careful. But the good thing is if you do have a situation like this, it is something that can be, in most instances, remedied with some careful engineering design. Now, something that's often very much ignored or misunderstood is the effect of having various ducted inlets and this concept of what we call a Vena Contractor. So if you look at the top here, on the top left, we've got a nice straight inlet coming in. Obviously that's nice and ideal for the fan. Now obviously the other option, if you don't have a big long inlet duct, you can have a nice swept curve bell mouth, also nice and good and efficient. Now what we need to be careful of is if you have a sudden reaction right at the end, it's going to reduce the performance here. Equally, you'll notice that when you have a sudden intake like this, you get a bit of a separation at the point here. Let me just highlight that. So you'll see in here and here, you actually get a net reduction or effectively a net reduction in cross-sectional area, which means the air has to accelerate, which is actually going to rob you of static head, which means your suction pressure, or your degree of vacuum, if you like, on the fan inlet is going to be a little bit higher, which means your fan's going to have to work that much harder. Now down here you'll see that we have the sudden inlet. If it's very short, it's going to have similar problems. Nice bell mouth here is going to be nice and smooth, and obviously you know, sort of 5 and 6 are the ideal scenarios. Now what's of course interesting is generally your fan intakes don't look like that, but see, this is where, as you're looking around, you can identify these opportunities, and there's something that generally are readily fixable. Now just on this, just to help us get our heads around it, we just want to stop for a minute here, okay, and understand what happens at the fan inlet. Now we did mention this previously in another webinar in terms of Bernoulli's equation. Now we're assuming here there's no change in height, so static pressure is total pressure, sorry, is equal to our static pressure plus our dynamic pressure. Now obviously the static pressure is the pressure of the stationary fluid. The dynamic pressure, of course, is the kinetic energy per unit volume of a moving fluid, or in the equation here, half times rho being the density times the velocity squared. Remembering, of course, that velocity is a vector quantity having both a magnitude and direction, and in ducts we'll have an axial component plus an in-plane component. So if we have x as our axial direction, our y and z in-plane components will actually contribute to the magnitude of our velocity and therefore the energy in the flow, but not necessarily to the actual volumetric flow rate, because obviously the volumetric flow rate is the actual velocity times the area. And so this is where, especially at the end of a fan coming out the outlet, you can have a higher kinetic energy in the flow, and obviously how we recover that, if we recover it and get that converted to static pressure, then that's a good efficient system. If we don't recover it that well, that can all get dissipated in turbulence and mixing, and ultimately result in inefficiency. So the primary function of the fan is to generate this dynamic pressure, and then subsequently the primary requirement of our fan housing and fan outlet, and then the subsequent ducting, is to maximize the conversion of that dynamic pressure into static pressure. And so static pressure recovery is going to be dependent on how we control the expansion of the gas stream, and obviously if we have poor duct design and poor layout, it's going to have a very low static pressure recovery and a whole lot of additional parasitic losses, which means that our fan is going to have to work that much harder. Now I've drawn an example here, and this is something to think about. We've talked previously when we talked about taking measurements in a fan system, and looking at static pressures are a good guide as to what's going on in the system. Now in most systems, so here's just a CAD schematic, if you will, of just a standard centrifugal fan with axial inlet and then obviously coming out the side here, and this is just showing a filter bank to the side. Now generally, if I get our highlighter out, we might have a point here where we take a static pressure reading after the filter bank. Now what that tells us is the pressure drop across the filter bank, but you'll notice that by virtue of it being a filter bank, we've deliberately got quite a large cross-sectional area to reduce our velocity so that our pressure drop across it is relatively modest. Now of course what happens as we reduce down our area and we actually look at the pressure right here at the fan intake, what you've got to be careful of is you do your measurement here, and that isn't actually the suction pressure of the fan. The suction pressure of the fan is actually what we've got here. Now when you think about this, so the question is well, what happens between here and there? Well, what we need to look at is what's happening to the dynamic pressure in the air. And so if we take at point 1 here at the just after the filter bank, we might have a 2 meter a second velocity. So at that filter bank, relatively low velocity, high area. Okay, whereas at the fan inlet, it's going to be a small area, high velocity. So velocity at this point here, number 2, might be say 30 meters a second. And so we actually can calculate or estimate, if you will, the change in pressure, which is a direct offset to the change in dynamic pressure in the flow. So it's just half rho V2 squared minus V1 squared. Now of course if we just take density of air at 1.15, 30 squared minus 2 squared, we end up with 515 pascals. So our suction pressure in this particular situation in front of the fan is going to be 515 pascals lower than what it is at our measuring point. So if we have a delta P across our filter bank of 150 pascals relative to the room next to this fan, our actual inlet pressure or suction pressure is going to be 665, possibly even lower depending on the losses in that duct in terms of how badly designed that transition piece could well be. So it can make quite a difference when you're doing your pressure measurements to calculate where you think you might be on a fan curve. If you're taking measurements here, and I certainly see a lot of facilities where that measuring point is here rather than right at the throat of the fan. And so you need to be very, very careful in making sure that you understand what's actually going on with the system. Now, another point to consider is not only do you have these variations, but you might also have some additional variation due to other parts of the system impacting on what's going on. So you need to be very, very careful when you're measuring these pressures that you understand what's going on and that you've compensated correctly. Now, another key example of this would actually be if you have some inlet guide vanes or some sort of butterfly. So you might have in this section of the duct here some guide vanes to throttle the fan. Now if you do that, if you take a measurement upstream of those fans, the way they are designed to work is to obviously throttle back the flow, which is going to cause a pressure drop. And obviously when you do that, once again you're not measuring the full suction pressure of the fan. So you need to be very, very careful when you take these measurements that you understand what's actually inside these ducts and what's going on. So just some more examples of upstream effects on fan intakes. So here you can see an elbow at the top there. There's a couple of ways we can resolve this. In an ideal world, to the right we can have a increase in the duct length, so have that elbow a long way upstream, preferably a couple of diameters away from the fan intake, which gives the flow a chance to spread out and reattach to the wall. Now if you can't do that, if you don't have the space, the other option, apologies, would be, would be to mitre that bend, and even better perhaps would be to mitre it with some flow control vanes to help the air around the corner. So flow straighteners can do an awful lot instead of having to replace a whole lot of ductwork. For smaller systems it's actually far more cost effective just to build a whole new duct piece and to turn around and say, you know what, we've got a flange here, we've got a flange here, let's just make a new piece and we can bolt off very, very quickly and easily. Often in a lot of cases you don't have the luxury of some distance like this, so alternative solutions need to be provided. But the key point here is that if I highlight this area here, especially if this velocity is quite high, there is no way the air can make that 90-degree bend, and so what you end up with is a hole, if you like, at the intake to the impeller. So as the fan impeller is rotating around past that point, the blades are going to start to stall, and then as it turns a little further it suddenly gets a whole heap of air, and so you're going to get all sorts of nasty imbalances on your impeller. The fan's going to run a little bit rough. It's going to put all sorts of vibration back down through your shaft. Depending on your bearings and everything else and what sort of condition they are, it can start to cause all sorts of trouble for you. Let me just clear those scribbles. Another really common problem that we see with duct design and troubleshooting with systems is where you have multiple ducts coming together. So often you'll see this where you have a single large air handling unit. It might be a big extraction fan or a big exhaust fan off a process. You might have multiple ducts feeding into a common system, and what you have to pay close attention to is when they come together, especially right in front of a fan like this, what ends up happening is obviously these flows are turbulent, and at any given time if you were to plot the velocity in this top one, it's not actually a straight line. It's going to end up doing this, and then at the same time you have another one here, and this is doing this, and it might not be in unison. And so what of course can end up happening instantaneously at any one given point in time, as it's shown here, the top or the bottom could be the dominant stream, and they are going to continue to fight backwards and forwards, backwards and forwards. Now what you want to do is actually put a dividing line in here. It's kind of a bit like for those of you that have got a couple of young kids and they've got to share a room. Sometimes you almost have to resort to putting a line down the middle and helping them have one side each. Sort of saves a whole lot of arguments, if you will. But there is some merit to this. If you think about this, and the way I like to describe it actually is, if you think about this as a multi-lane highway coming together at a big intersection, and they both want to go the same way. Now if this was a T-junction and you got people wanting to turn left from coming up the top, and then the people from the bottom wanting to turn right, okay, well what you actually need to do is, if you divide that road for the first little bit, then both sides can turn into the corner and then they can merge as they're already pointing in the same direction. So airflow very much the same way. If you can divide them and bring them in together, it's a lot more smooth, and instantaneously that turbulence doesn't fight each other anywhere near as much. So it's just, if you stop to visualize what's actually going on and what you're asking the air to do, there's some fairly simple, basic, common sense solutions that can resolve a lot of these issues. Now another common problem that we see is where you have multiple fans together in a room, and you might have inlets that are opposite one another. And so as a general rule of thumb, and once again there's a lot of design engineers out there that either A, don't know, or B, haven't taken the opportunity to avail themselves of what they should do. But so that you know, and so you can point these things out, know to ask the right questions. If you have two opposing inlets here into two fans, as an absolute minimum, you want 2 diameters separation between the two. Any less than that, you're going to have the two inlets are going to start fighting each other. And as you reduce that distance, the effect in terms of pressure reduction, all the rest of it, gets more and more pronounced. So just really important. It really is common sense, but it's amazing how uncommon common sense can be. Now the other thing, of course, is when you have multiple fans with common enclosures, we should be separated, as we're saying, and then obviously you want to have equal spacing so that you've got air going to all the fans. Now often many of you will have systems where your fans aren't actually all the same size, and so this is where you want to make sure that you've got plenty of plenum space in that fan room, so that you don't have any one fan hogging all of the air, so that you've got good even distribution. So as a general rule of thumb, you want to make sure that you've got a decent volume of air in that room, so that you're not drawing the air down too quickly. So you can start talking in terms of air changes an hour, if you will, which is certainly more of a HVAC term than a process air fan term. But yeah, so you do want to be careful that your velocities in the room should be sort of under 1 meter a second. And obviously as it gets closer to the fan itself, they'll accelerate up, and it's not uncommon to have 20, 30, 40 meters a second at the actual fan inlet itself. Now that's okay, but you don't want to have high velocities in the actual room blowing, having to get the air to where it needs to go. So you really do want that under 1, maybe at an absolute stretch 2, but ideally below 1 meter a second. Now on the exit side of the fan, now if we look at the fan exit side of the equation, as you can see, if you look at the fan exit right here, we have a very uneven distribution, and it takes a number of diameters for that airflow to even out. Now there's a great chart that you can refer to, okay, and there's a fancy equation there, but generally speaking, the effective number of duct diameters you need to get good velocity distribution is actually a function of velocity. So if I just highlight this point, so if you're at 10 meters a second, you can probably get away with 2.5 duct diameters. If you're out at 30 meters a second, you're now at 6 duct diameters. So you can see that the faster the airflow, the more duct you need, which kind of makes sense. It's kind of a really good analogy. If I come back to my highway and cars on the highway analogy, the reality is if you're a domestic street, you know, and you've got a 50k an hour speed limit, you know, probably don't need as much space to stop or to change direction, to turn. Now you can probably turn quite tight. Now if you're on a main highway, you really do want to have more room to either stop, or if you're making a big bend, you don't want to go along the highway at 90 kilometers an hour and hit a 90-degree bend. You want that bend to be a nice sweeping curved bend, bit of camber on it to help you to get around the corner nice and safely and smoothly. So same thing with the airflow. It doesn't like changing direction very easily, so the higher the velocity, the more room it needs if you want it to spread out nicely. So here's another example where, and we see this all too often, immediately after a fan we might have a fan that's feeding multiple ducts. Very common in the HVAC industry to see this sort of thing. Also just process air ducts. For those of you with factories, you might have ventilation air for your building will generally have these sorts of crazy designs as well. If you're not careful, I know this sort of thing happens. A number of pulp dryers up and down the country have very tight ducts in between fans and where air's got to go. So yeah, it certainly applies to quite a few installations up and down the country. Certainly plenty of milk dryers with this sort of thing happening as well. And so what we're talking about here is we've got the air coming out of the fan, and of course we can have the offtake. Now the problem is if the offtake is too close to the fan, then that can cause all sorts of problems. Now the other thing of course is that we haven't shown on this picture, but I'll highlight it at this point. If the air is rotating like so, the last thing we want to do is to have our offtake over here. So at least in this situation they've got the offtake going the correct way as opposed to the incorrect way, but ideally you want to be further away so that you've got time for that flow coming off the fan to even itself out. Generally speaking, the amount of air on this far side here is going to be a lot higher than on the inside, and so you do need to be careful. You can get quite uneven distribution of airflow. Now there might be instances where you're happy for that flow to be uneven and you might deliberately build that into your design, but you want to be very, very careful and know what you're doing if you're playing those sorts of games. So here's sort of a good example in terms of the rotation of the fan. So the one on the left, obviously the fan's rotating counterclockwise, and then it comes out straight into what's effectively a clockwise elbow. So that's actually going to do a couple of things. It's going to directly impact on the performance of the fan, and then it's also going to have a higher static pressure loss across it, and then obviously the profile across the outlet there. This is heading into some sort of piece of process equipment. You're going to have other issues. Most of the air is going to be up here. There's going to be none down here. And so depending on what that's coupled to, that could create all sorts of other problems. Now in this scenario on the right, you've got the fan still rotating counterclockwise, but with the counterclockwise elbow, you know, the flow is going to actually want to make that bend, and so you'll have a much better distribution coming around this bend. Now what's worth pointing out at this point is that this fan here could equally, at the stroke of a pen when it was purchased, be purchased with the housing orientated the other way. The placement of the impeller, the location of the motor stand, all of those things can be set when you order these fans, so it's very, very important that, that these things can be corrected. The other thing you could do is look at just reconfiguring the fan housing and so on. And obviously the other thing too to bear in mind is it's not unreasonable for that whole fan to be actually rotated 90 degrees, and it could be feeding straight out on its side as opposed to vertically up, vertically down. And you can actually almost specify, if you're using a reputable fan supply, any angle for that outlet of the fan in the housing within reason. Obviously if you want a very particular angle you might have to pay a little premium for it, but all these sorts of things are quite easily done at the design stage. So as a bit of a good summary here, your critical fan inlet and outlet duct design solutions. You want good even flow to the fan with minimal rotation. When you have rotation, you want to align the fan and duct correctly. Fans can be supplied, as we just talked about, with the correct orientation and correct rotation. Understand the difference between open and closed inlets. Where does the air go? Visualize how the air is going to make bends in the duct, how it's going to transition. Understand that air isn't going to make a sudden change in direction unless it's going incredibly slowly. You want to watch out for intersecting ducts. Think about how the air is going to mix. Look at aligning flows as opposed to competing head-on. So just as another point to look at some of the indirect losses now in terms of duct design, we can have poor airflow into or out of process unit operation. So this is, for example, heaters, coolers, reaction vessels and so forth. And any poor airflow in and out of these processes will compromise their performance. So ducting will directly increase static pressure drop, but generally bad ducting is also going to result in flow maldistribution. And when you have that, you're going to have an actual process performance that can be significantly impaired. So examples of that: temperature profiles, humidity variation. You can impact on product quality, process control, the stability of your system and your process. Ultimately then the yield in terms of how well you can run the plant. You might have to run it back a little bit to stop it from blocking or other things going wrong. You can run up against environmental emissions problems if your cyclones aren't working correctly because they've got poor airflow distribution, or your fans have been incorrectly matched to your cyclones. You can then end up with excessive emissions. Certainly, if not on regular running, at startup and shutdown can become an issue. Ultimately, what all of this leads to is increased plant risk factors, be it safety, stability and control. And there are some energy penalties, but to be brutally frank, although obviously everything that we talk about is by and large under the guise of sort of energy and energy efficiency, the reality is most of these other issues that I've highlighted there are at least an order of magnitude, if not 2 orders of magnitude more costly than the energy savings associated with getting the design right. Now, the benefit of that, of course, is that provides you with plenty of ammunition to justify fixing some of these problems. So this is sort of a real old school picture straight out of an aerodynamic textbook. So you can therefore your airflow's coming down a duct, you've got a mitered bend, fairly stock standard. You see this sort of duct transition up and down the country all over the place. And what you'll see is when we hit this transition, you'll notice the airflow's coming down, down, down. And of course what's happening is 2 things. The flow's wanting to short circuit the corner obviously, but it is actually detaching. And you get this eddy zone in here. Now of course what happens is, if we have, I'm just going to change to my, my spotlight here. If our flow and everything else is down here, then we can get away with this by and large. It's sort of not going to cost us a huge amount. However, if because of space constraints, our fan inlet is right here, or even worse, perhaps right here, we can have quite a big gap in our intake to our fan and cause all sorts of issues and challenges. And so you want to be very, very careful in looking at bends, where they are often placed and how they're radiused. Now, as a general rule of thumb, with a miter bend, does that bend need to be a nice, even, curved, swept elbow? Well, if it can be, great. However, if you have a 3 or 4 piece lobster back or miter bend, as opposed to that 1 miter bend, you'll find that just 1 or 2 extra miters on that bend will make the world of difference to the flow around it without having the expense of a fully swept, curved elbow. Okay, so duct transition, same sort of scenario. As we increase this angle, we get a bigger and bigger eddy zone, which means we get worse and worse distribution across our heater or some other process device that we might be using. So heat exchangers, filters, dryers, fluidized beds, attenuators, etc. Now, incorrect design of these expansion transitions can cause significant losses, not just in terms of energy and poor static pressure recovery, but also in terms of the performance of the system. Now, contractions at the other side of things aren't generally as bad, but a sudden contraction should still be avoided. So here's an example of you've got a sort of a 9-to-1 area ratio expanding out. You can see that depending on different scenarios, we can put a bit of back pressure on, but we still don't actually get the flow distributing out. So looking at flow expanding in a rather large diffuser like this, you can get a concentration of the flow in the middle and sort of not a lot of flow around the edges. Now, depending on the geometry, you can get some rather interesting outcomes. Now, there's a chart here that we can refer to in terms of area ratios and length, which is ultimately then the angle, which is defined as twice the angle here. And you can see that once you get up to sort of 45 degrees, or i.e. a 90-degree diffuser, you start to get up into this regime here, which is where you get jet flow. Then you get sort of, as you reduce that angle, you can get sort of the flow tends to stick to one side. Then it can actually flip-flop from side to side, and then actually if you reduce the angle enough, of course you can get nice even airflow. Now, of course, the problem with this is any real-world application, you all end up being, if I get my highlighter out here again, up in this region of the curve as opposed to down here. It's just not economic to be there in most instances, and so it's a question of what you do to cope with that, and there are strategies that you can put in place to do so. Now, of course, noise control, you'll see that you've got these attenuators should be a reasonable distance away from the fan to give the flow a chance to settle down. You don't want them vertically around an elbow like this. Obviously, all the air is going to go around the outside. By having them horizontal like this, you can have the air spread as it goes through the attenuator. So here's an industrial air heater example. I think I may have shown you this picture before. We've got our fan here, diffuser, heater, and then a contraction before this air goes into, in this case, a milk dryer. We've talked about a fan profile coming off the fan here. Obviously, the geometry is a key input. The resistance of the heat exchanger is also an input. It's not necessarily going to be uniform, and then obviously the fan profile is going to dictate what happens. Now, what I want to do is I've actually wanted to simplify this example for you, and if you actually look at this duct, and this is what we want you to be able to do as you're going out and looking at your systems, what I want you to be able to recognize is the number one problem with this setup is actually, well, first of all, I'm going to highlight here, our profile coming out of the fan housing in black, so this is our fan housing up here, okay, is not going to be uniform. It's going to be biased to the top. Now, obviously, what then happens if I get those markings out of the way, when we get to the fan transition where we now go into the diffuser, you'll note in this particular installation that the lower edge of the diffuser follows nicely the fan outlet duct, whereas the upper end of the diffuser goes off at a rather sharp, nasty angle. And so what tends to happen in this instance is the air goes past there, it can't stay attached to this edge, and so it actually separates. And what happens with that separating, you end to get a eddy induced in the flow here, which actually helps to reinforce this flow going down. And obviously, because this duct is continuing on, the air likes to stay attached, and so you ultimately end up with all the air going down to the bottom and a big dead zone up in this top area here. So it's a couple rules of thumb to really live by when you're looking around for what's wrong with your system. Key point to start is understand the geometry of the duct and your system, and look at how the airflow is going to interact with that. So any sudden change in duct walls is bad. It's going to trigger flow separation. Your fan profile is also going to have an impact. You also need to remember, I've simplified it down here. This is a two-dimensional case. In the real world, of course, geometry is going to have 3 dimensions. And of course, the added reality is there's always the 4th dimension, which is time. And of course, with these flows, it's certainly most industrial, even HVAC in buildings and the like, these flows are all going to be turbulent, meaning at any one instant in time, the flow is going to be varying. And so in addition to the geometry, you've got the flow, which is ultimately going to be unsteady and changing. Over time, it will most likely be statistically steady, i.e. you'll be able to get an average flow with some sort of fluctuating component, but by and large, instantaneously that's going to be going up and down, and that is going to interact with your geometry and everything else in the system. But you can probably, in the first instance, not concern yourself with how things are going up and down, but if you just looked for areas like this where one of the key points here would be is without any intervention, you are always going to have a problem with a change in direction like we've got there. So you're going to have to control the airflow around that bend if you want the air to actually make that bend. And so we've shown you this picture before in a previous webinar, and this is where we've had 2 heaters stacked on top of each other, and the flow, because of the sudden change coming up here, tends to separate and go down, which meant this top heater didn't do a heck of a lot. So what of course you can do is with the right design, we can spread that flow out and evenly distribute it across the heater works a whole lot better. So here's sort of a shot of some of these vanes sitting in a duct and what they look like. So in this example, we can control the flow despite the rather nasty duct transitions. And the outcome of that is we get a lower pressure drop, we get an increased static pressure recovery. And so in an industrial situation like this, you've got a couple of options. You can reduce your fan power consumption, you can increase your airflow, or a combination of the two, which will ultimately give you the option to have some more production capacity. What it will also do is lower your velocities across your heat exchanger. You'll get more uniform flow, which is good for your condensate loading on your coils. You'll get a much more uniform condensate temperature, and obviously you can ultimately lead yourself to lower steam usage. And depending on whether you're using orifice plates as traps or actual steam traps, that can vary wildly. We've seen those sort of steam savings be up at sort of 10-15%. It's not uncommon to sort of see a 5-6% change. In fact, we just recently were involved with a project on a heater here in New Zealand where the airflow was not very well distributed, and we've dropped the condensate temperature off the heater down by over 30 degrees, and the steam pressure required to get the production capacity of that plant has gone from 22 bar down to about 11 bar. So obviously everything's not working anywhere as hard, nothing's as stressed as much as it used to be. The condensate's nicely subcooled, so you actually use less steam, but you're using more energy out of the steam. But the big benefit in a situation like that is where you would have flash steam going down to your condensate tank and then flashing off and out of vent. All that steam has been condensed and subcooled, so there's no losses at the condensate tank. So you actually start to really save energy in that there's energy that's not being vented somewhere. So in these cases, the flow-on effects for doing this right can be substantial, and it's not uncommon on an air heater like that. Those savings can very quickly sort of get up into the hundreds of thousands of dollars. Sort of looking at a couple of fluidized bed examples very quickly to finish off today. So here's the static fluid bed, air coming in underneath the bed, which is shown in red. Now what I've got is we've actually prepared earlier a video that we want to show, and so we're just going to bring it over here. Okay, so just, it's not playing ball. Okay, so hopefully that's going to work. So if we hit, it's going to take a while to catch up. Computer's struggling a little bit. Is that coming through? Ooh, the computer's frozen on me. Okay, we might kill that. We'll close that program. Okay, we'll try that again. Okay, there we go. So what we've got here is the flows coming underneath the bed, and it's actually it's sort of offset and it's got an imbalance in it. It's what you end up with as the flow comes around, and you get a dead spot over here and a high spot over here. And so you can see that for a bed like this, you're going to have quite an imbalance on the bed, which is going to cause problems in terms of uniformity of what's going on in that bed. So if you've got a reaction taking place, or it might be that you're trying to dry a product in that bed, you can ultimately compromise your process if you're not careful. And so what we would then do is if you actually straighten that out, you can end up with a really good unsteady but statistically steady distribution of airflow across that bed, which is going to give really good mixing and ensure that that actually works really well. And so this is just a really good example of A, poor duct design, and B, if you rectify that duct design. We've recently done a project where we haven't actually changed the geometry itself, but just by the careful design and placement of some control vanes to control how the airflow comes in underneath the bed, these problems can be fixed. So what we'll do is we'll switch back here, slideshow, current slide. Okay, and so to sort of demonstrate what we're talking about here, if we get the flow delivery to a large open cavity, like underneath a bed like this, for example, you need to consider what downstream resistance is going to spread the flow. Now, a lot of people make the mistake that, oh, we've got plenty of back pressure, so the flow will spread naturally. Now, that may be the case, it might not. You can understand the difference between constant and variable resistance, but equally understand how do you get the air from where it's coming in to where it needs to go out. There's a magnitude to the resistance in comparison to the dynamic pressure of the air, okay, and how much force is there spreading the flow, what direction is it in, and how does that relate to where the flow is going. There's going to be jets that are naturally biased in one direction. Now you can use that to your advantage in certain situations. Other cases you might need to eliminate it. So obviously the geometry plays a big role, and you need to be very, very careful on how you resolve these sorts of challenges. Very important to get the design right. So when you're considering the final process unit in the context of the fan system, you want to be very careful in thinking about upstream ducting design, flow maldistribution, especially in terms of heat and mass transfer. You might get excess gas flow to one part, which is compensated for by low flow somewhere else. You can get unstable jetting, and what that can do is it can mean that you have too much product being carried over into the exhaust stream, which can cause either product losses or contamination or other challenges. You could have surging on the fan as loads vary. You could have localized temperature fluctuations, or in some cases what's much worse is localized humidity fluctuations, which if you're dealing with a drying process can cause you all sorts of quality and process challenges. Now here's another example of something that's been modified recently. You'll notice that we've got a what was a T-piece round duct here, air coming into the side of a bed and then coming up. Now of course what you'll appreciate is you know, the flows up here are peaking at 44 meters a second, which, to give you some context, that's sort of 160, 170 kilometers an hour, certainly getting right up there, well certainly you know, 150, 160 kilometers an hour. And so of course what happens is that air has not even, you know, fractions of a second to get from here to where it's going, and it's not going to make a U-bend and come around. And so you can fix this elbow, which has reduced the airflow a little bit, but then ultimately what we ended up doing is, by some careful treatment of the flow, we can spread that across that bed. Now, of course, what we've deliberately done here is we've given no bias to any spreading from pressure drop across a bed plate in there, and we've done that very deliberately, and I'll explain a little bit more about that in a minute. But what were the results and outcome of this? We had a total static pressure loss reduction of 1400 pascals, which is about 35 to 40% of the system. There was some energy savings, but the big benefits was around the performance of the fluidized bed, how quickly it got started, and then of course even flow, even process means it's much easier to control and manage what you're doing. Now, I want to talk about some very important cautions at this point when it comes to using CFD and other general troubleshooting. As we've just shown you with these pictures, it's very easy to generate some pretty pictures, but it's very important that you don't blindly trust the solution. I could have equally set those models up, put some back pressure across that plate and delivered you a nice even distribution of airflow. Now we know that that doesn't actually happen in practice, and the reason for that is these commercial CFD codes tend to artificially spread uneven flows. It's particularly pertinent when things are uneven, because of the way the code solves the physics. There's approximations that are made that actually start to drive the solution instead of calculating what actually takes place. If anyone's interested, I'm happy to have an offline conversation with you to discuss that further, and by all means just send me an email. Just a reminder that 27.8 meters a second is 100 kilometers an hour. Air's not going to turn corners easily, and any sudden change in direction will most likely induce flow separation. It's going to increase turbulence and will generate dead spots, and that's particularly relevant under fluidized beds and such. So in summary, to finish off today, the fan inlet conditions can have a significant impact on fan performance. 15 to 30% reduction efficiency is not uncommon or unheard of. Fan exit conditions will also result in poor flow distribution and suboptimal dynamic pressure recovery. You'll get flow separation, okay, and will impact on downstream processes. Duct design is crucial to maximizing system efficiency and minimizing static pressure losses. Now, duct design will impact on the system performance both directly and indirectly, and I'm repeating myself a little bit here, but very deliberately so. And that is directly, obviously, higher static pressure loss, which is a higher energy loss and may well impact on our fan efficiency. Indirect, though, you're going to have an impact on the efficiency and effectiveness of your process equipment. So things like the utilization of heat exchangers, if you've got poor airflow distribution across them, that can be diminished. Heaters, coolers, dryers, fluidized beds, all of these processes can be impacted. And so in summary, very, very important that you want to pay close attention to where your ducts are, what they look like. And the key things to look for is really measuring your static pressure to understand where you're losing static pressure, and then obviously looking at your duct transition sections and any change in direction. As a general rule of thumb, if you're losing more than a couple of hundred pascals across your duct work, you've got a problem and you need to look at it. I've on numerous occasions come across 1,000, 1,500, 2,000 pascals drop across some innocuous ductwork. That tells you you've got a problem in terms of troubleshooting. Now, it might need to dig a little deeper to figure out what's going on, but if you're more than 100, 150, 200 pascals tops on some decent ductwork, you've generally got something going on that you need to be worried about. And it's very, very easy to have those sorts of losses, but as we've demonstrated with a couple of those examples today, easily rectifiable. Now, to finish off, we've got some webinars coming up. The 5th and 19th of October, we'll confirm those topics in the next week or two. Our website there is going to have the registration links, and obviously the webinar from today will be on the EcoBusiness YouTube channel. Don't forget that you can get advice from your ECA account managers. There's advice also on the ECA website. You can look at our website, energyefficiencyedzen.com. Feel free to email me, jamesn@waikato, and there's a number of really good fan system books out there that are available free off the web for anyone that's looking for some light reading to look a little further. So that really wraps up our webinar today. So I'm happy to field any questions that some of you might have. Alternately, if you need to go, because we've certainly used our time today, by all means feel free to email me. Once again, the email address there, jamesn@waikato. We will stay on the line for a few minutes to give you guys a chance to fire in some questions. Otherwise, we will see you in 2 weeks' time. And that'll be the Flash, no, sorry, not Flash Steam, it's the Waterhammer webinar in 2 weeks' time. That registration link is on our website for anyone wanting to register for that. Okay, we'll give you a couple more minutes to fire in a question, otherwise we'll see you all next time.